Hello and welcome to this video on evaluating expressions of the form a to the m over n power. That's a base of a and a fraction exponent, m over n, or m-nth power. And what we're going to do in this video is I'm going to go over some properties at first that you'll probably have to remember, some properties of exponents. And also in a previous video I discussed the relationship between radicals and fraction powers. We're going to discuss that a little bit too. And then go into several examples involving those properties and taking an expression of this form, writing it one as a radical, or taking a radical and writing it in this form, a to the m over n, and then of course simplifying it, stating the value of this of each expression. Alright, so let me begin by starting off with some properties. We need to know properties of exponents and a relationship between radicals and rational powers. So again, just a couple. These aren't all the properties of exponents, and again, if you can look up videos on properties of exponents if you want to see them all in more detail. I'm just going over a couple that we should know for the rest of this video to help us out. Right, so some properties of exponents, powers. Alright, so one of them that's going to be used a lot is the power to a power rule. I guess you could say that I'll call it the power to a power property. And I even had this one up in my last video on evaluating expressions of the form a to the 1 over n, not just a to the m over n. So the power to a power property is the following. If you have a base a, use lowercase a. If you take a number a and raise it to, say, the mth power. Alright, so it's base a to the exponent m. And then you take this expression and make it the base, right, so put it in parentheses here, make it the base on another exponent. Say the other exponent is n. This will be equivalent to your original base. You can keep the original base, base a, and the new exponent on this base of a will be the product of these two, m times n, or just simply written as a to the mn. Right, that's m times n. All right, so this is gonna come into play during this video. Another property that's going to come into play is a negative exponent rule. We're not going to come across this until the last couple examples in my video here. But the negative exponent rule, that is, if I have a number, some base, again I'll use a, to a negative exponent, right? So I'll put a negative in, right? So suppose n is a positive number, and then I make it negative by throwing a minus 1 and a negative sign in front of it. Alright, this is equivalent to the reciprocal of the positive power. Alright, so a to the negative n is just 1 over, right, is the reciprocal of 1 over a to the, just positive n. Alright, and we're going to see this rule will hold for fractions. Additionally, right, or we could think of it this way too. If I want a to the n, I could take the, a to a positive power is just the reciprocal 1 over the negative power, a to the negative n. Right? These mean the same thing. All right. If you want something to a negative power, take the reciprocal of the positive power. And for some reason, you could also do this. If you have a positive power, you can just take the reciprocal of that same base to the, the opposite power, the negative power. All And then one little recall from the last video. So those are the two properties of exponents I'm going to need for this video. And one recall from the last video is that when you see the nth root, right, this is a radical symbol, root symbol, and index of n. When you see the nth root of some number a, that is equivalent to, taking that radicand, the a, making it the base a, raised to a power, and the power will be the reciprocal of the index. So if the index is n, the exponent on the base of a is 1 over n, and again this is as long as that nth root of a is real. Okay, because we've seen other videos, when you have an even root of a negative radicand, an even root of a negative number, that's not resulting in a real number. All right. But anything else, an even root, square root, fourth root, etc. of a positive number, or 0, a non-negative number, will result in a non-negative number. And odd roots, cube root, fifth root, seventh root, etc., of a positive number will result in a positive number. Cube root, fifth root, seventh root, an odd root of a negative number will result in a negative number. And also the odd root of 0. Any root of 0 is just 0. Okay, so keep in mind this relationship here too, that you can take one of these radicals and write it as, the radicand a to a fractional power 1 over n, where n is the index of the radical. Alright, so I'm going to keep all this in mind. To get to our expressions of the following form, right? The title of the video is Evaluating Expressions of this form here. This is some number a, base a, to the, and then a fraction power, m in the numerator, n in the denominator. All right. Well, you can look at this in a couple ways. We can think of this as, and this is going back to I'm going to bring this up, that power to a power property. You can think of m divided by n as m times 1 over n, can't you? All right, remember this is like m over 1 times 1 over n, and when you multiply two fractions, you just multiply the numerators, multiply the denominators. This would be m in the numerator and n in the denominator. So these are the same. And now I have this base to a product, which is exactly like the right side of my property here. When I have a base to a product, we can write this as something to a power and then again to another power. This would be equal to a to the mth power, in parentheses, that's the base, raised to the 1 over n power. All right. Okay. And then tying in, now that I have some number to the 1 over n, I can use this relationship I mentioned. When you see a something to the 1 over n, that's exactly the same as a radical. All right. So what we're seeing here is that when I have a to a fraction, a to the m over n, it's exactly the same as the nth root, right? When I have a 1 over n power, that's the nth root, right, index of n, of this base, this a to the mth power on the inside. Right. So I'll put this in a box. All right, this is a nice important relationship. Right, so when you see a fraction for a power, you can write it as a radical. But also, right, not only can I think of the fraction m over n as m times 1 over n, you can think of it the other way, right? I can switch the order of these two factors. So we could also think of a to the m over n as a to the 1 over n times m, right? Isn't that the same thing as m times 1 over n would be the same as 1 over n times n? All I did was switch the order of the factors, and the real numbers have the commutative property, right? You can switch the order of factors and it'll still be the same number. And then here I have a base to an exponent that's a product, just like up here. And so I should be able to write it like this, with a power to a power, but this time the inside power will be 1 over n, and the outside power will be this m. So I can write this as a to the 1 over n, and then raised to the mth power. And just as before, look inside the parentheses now. You see I have an expression a to the 1 over n. I can write that as a radical, right? That's this relationship here. Whenever you see an expression to the 1 over n, you can write that as a radical. Okay, so we're also seeing, not only can I write a to the m over n as the nth root of a to the mth, where the m is on the inside, but I can also say that a to the m over n is equal to, and then you see how this is the nth root of a as the base, right? A to the 1 over n is the nth root of a, okay? That's a to the 1 over n, and then that to the outside power, right, to the mth. All right, and this is also good. This is just another way to see the same expression. Now, of course, these are only any good provided that the nth root of a is real, right, is a real number. All right, then we can use these properties, this relationship. All right, because if this was an even, if this was the square root of -5, right? Remember, the square root of an even root of a negative number is not real. Then we couldn't even evaluate this. All right. So yeah, so what you're going to be looking at is, the denominator, right? The denominator of the fraction power, the denominator tells you the index of the root, right? The denominator of the fraction exponent tells you the index of the radical in your radical expression. All right, so if you look at your denominator and it's even, right, 2, 4, 6, 8, but your base is negative, right? If the denominator is even, but this a, the base is negative, then we can evaluate this. This won't be a real number. All right, because if you have an even index, an even root, you better be taking the even root of a non-negative number. Right? So if the denominator is even, a needs to be greater than or equal to 0. If the denominator is odd on these powers, then the base can be anything. Right? You've seen in previous videos, when you have an odd root, you can take an odd root of a positive number, a negative number, or a 0. It doesn't matter. It will always yield some real number. Okay, so I'm going to keep these in mind, right? And now let's work on some examples where I'm taking an expression with one of these. I'll go both ways, or we'll go in both directions. Where I'm looking at an expression with a fraction power, and I'm going to write it as a radical, and I'll show you both, and really they give you the same thing, right? We'll see that they give you the same thing. Both of these mean the same thing, and we can decide which one's easier to help us evaluate a number, right? Evaluate an expression. All right, so my first example, and each one following has the same instructions. I have evaluate each expression, if possible, if it's real, right? If it's a real number. So notice here, I have 16 for the base on this power of 3/2. Look at the denominator. The denominator is an even number, and the base on this power is 16. The base is non-negative. right? The base is not negative. So this is a real number, right? This 16 to the 3 halves is going to be a real number. So let's try to find that. What number is it, right? What number is it equal to? All right. So as I said, I'll go through both, right? So let's look at this first one here. So we can think of, 16 to the 3 halves as, this is, again, the denominator is 2. So we can think of it as the square root of 6, and then inside we have the a to the mth. I take the square root of, and then on the inside, 16 to the 3rd power, the base to that numerator power. All right, so the denominator is the index 2. The numerator of that power is the power on the inside when I look at it this way, this first way. All right, and then I'll use a calculator here. But we have the square root. What is 16 to the 3rd power? All right, so this is square root of, and then 16 to the 3rd power is 4,096. That's 16 times 16 times 16. And then the square root of this number, the square root of 4,096. Remember, when you see an even root, right, an even indexed root, that's asking for the principal square root, the non-negative one, because this is positive 64, right? Because 64 squared, 64 times 64 is 4,096, and again, I just kind of punched that in the calculator really quick. Yeah, and I know negative 64 times negative 64 is also positive 4,086, but again, I will say this a lot, and I've said this a lot in previous videos. When you see this symbol with an even index, they're asking for the non-negative root. Okay. Great, so 16 to the 3 halves power is 64, and if you'd like to check that, you can go to a calculator. Lots of calculators have power features, raising the powers. I'll just throw this one up here. I got TA84. If I take 16, little caret button, right, raise 2, and then in the power, the 3 divided by 2, the 3 halves power, you're going to see come back at me the number 64. Right. It worked. It's real. It's positive 64. Great. All right, so I guess I could call that method number 1, but we could also look at it this way. The other way I had up here, instead of the nth root of a to the mth, where the m is on the inside, I can also think of it this way. Right, this second box that I put up on the last page. We could say that 16 to the 3 halves power is, and then as the base, take the nth root of a. Right? Again, the index is the denominator. It's 2 here. So take the square root of the base. Take the square root of 16 first, and then raise to that numerator power on the outside. This is the nth root of a, to the mth, where I have, the denominator is the index of the radical, and then the numerator is the power on the outside. So like that first way, right, I took 16 to the 3rd first. I did 16 to the numerator, and then did the square root, right? Got some large number, and then the square root got 64. This way is the other way around. I work with the denominator first. Take the square root, right? See, the denominator is 2. It tells me square root. Take the square root of the base first. Square root of 16 is 4, and then raise to the numerator power. All right, so let's go through, right? What is the square root of 16? That's positive 4. And then we're raising to that numerator of the power, 4 to the 3rd. And what's 4 to the 3rd? That's 4 times 4 times 4. That is 64. Exactly the same thing as I got earlier, right? Because they are, these two boxes here that I put up in the last page, these are the same thing. They mean the same thing. They'll give me the same number. Okay, wonderful. Now I actually prefer this second method. I prefer that because, when you take the root of the base first, that ends up with a smaller number, and then you raise to the numerator of the power. The other way around, when I did 16 to the third first, gave me some really large number. And I wouldn't want to do that by hand. 16 times 16 times 16. It might not take that long, but still, it ends up with larger numbers than I'd like. So I actually prefer myself personally, taking the root first, using the denominator first, and then raising to that numerator power. All right. Okay, so let's do that again. And again, I'll show you both methods, and you'll see again why I like that second way better. So here I'm asked to again evaluate, if possible, 27 to the 2/3 power. Notice the denominator on that power is an odd number. So we're good, right? You can take an odd root of anything. So this is a real number. It's going to be real, and we can continue. Great. All right, so the first way to look at it, I'll do that first one again, where when I see 27 to the 2/3 power, you can take the cube root. Remember that denominator is the index of the radical of 27 squared, right? 27 to the numerator power on the inside. All right, now 27 squared is again going to be some pretty reasonably large number. Not that big, but it's bigger than I'd like. That's the cube root. And here we're doing 27 squared on the inside. That's 729. Right? And then, what to the third power is 729? That's 9. Right? The cube root of 729 is the number 9. All right? So 27 to the 2/3 power is 9. Okay. But you could also do it this way. Right? Say you take your 27 to the 2/3, and instead of taking the cube root of 27 to the second on the inside, we take the cube root, again denominator is 3, so the index on the radical is 3, cube root, take the cube root of the base, right, the cube root of 27, and then afterwards raise to that numerator power. Put the square on the outside instead of on the inside. And this helps me deal with actually smaller numbers as we go through. Right? Because what is the base here? What is the cube root of 27? That would be 3, right? 3 to the third is 27. And then we're squaring this, and what is 3 to the second? What's 3 times 3? That is 9 again. Get exactly the same thing either way. Right, so, and you don't have to do both, right? Notice I put the word or here. You don't have to do both. Right? Just do one, and you'll get the correct value. And if you want to double check yourself, right? Maybe punch it in a calculator just to see what's 27 raised to the 2/3 power, and you're seeing the number 9 pop back there. Great. All right. All right. Next example, same thing. I'm asked to evaluate this. An expression with a fraction power in it. Now be careful with stuff like this. I've had an example like this on previous videos. Notice how there's no parentheses around -16, right? This is actually totally different from the following. So over here, what if I had the parentheses around the negative and had -16 in parentheses, then to the 3/4 power? Okay. These are totally different. Here, the negative sign is like having, anytime you see a minus sign, it's like having a factor of -1. So this expression that I started with, this negative, 16 to the 3/4, I see this minus sign out front with no parentheses. This is like having -1 out front, then times, and then 16 to the 3/4 power. Okay, so in this expression, under the exponent of 3/4, the base is just the number 16. The base on that exponent of 3/4 is just 16, not negative 16. Whereas over here, with the parentheses around it, the whole thing, the negative is part of the 16 now. Right? It's collected by the parentheses. In this expression, the base on the exponent of 3/4 is negative 16, not just 16. All right. So if you look further at this one over on the right side here, this negative 16 in parentheses to the 3/4 power, see the denominator is even, right? So I'd be taking a 4th root, right? That's going to be the index of the radical, index of the root. So I'll be taking a 4th root, and the base is negative. An even root of a negative number. The expression on this side is not a real number. Because you're taking an even root of a negative number. Not real. But on the one we were given, this -1 or minus 16 to the 3/4, again I'm seeing on the power here, the denominator is even, right? It's 4. So I'm taking an even root, but the base is positive. Right? The base is a positive 16. So this is a real number. Right? So this expression, this will be a real number, and then multiplying by -1 will still be real. This is a real number. We can find its value. So notice the difference, please, right? Just a little simple adding of parentheses changes the meaning entirely from something that is real to something that ends up not being a real number. Okay. So this time I'm going to do it the way I like, this shorter way with this. They're not shorter, but like the one where the smaller numbers are involved. All right. So this negative 16 to the 3/4 is, again, anytime you see a minus sign on its own with no parentheses connecting it to anything, that's a factor of -1 times. And then the 16 to the 3/4 I'm going to rewrite as a radical. Denominator is 4, so I'll be taking the 4th root of 16, right, the 4th root of 16, and then raising that 4th root of 16 to the 3rd power, right, put 3 outside. All right, so I have, again, that minus sign, that factor of -1 is still there, times, and then what is the 4th root of 16? What to the 4th power is 16? Well, 2 or -2, but again, this is, when you see this symbol with an even root, they want the non-negative one. It's the non-negative root. So that's +2, right, because 2 to the 4th is 16, and then we're raising that to the 3rd power. And then what is 2 to the 3rd? That's 8 times -1. This is -8. All right, so the value is -8. And again, you can punch this in just to check it. Let me see here. And in fact, I'll punch both these in just to show you that, again, there is a big difference. All right, so the first one, just a minus sign, and then times 16 raised to the 3/4 power, and you're going to see -8 come back, right? We said it was -8. But now if I put the parentheses around -16, like this expression on the right side of the page, parentheses around -16 raised to the 3/4 power, and look at what happens. See, error, non-real answers, right? Not a real number, and you'll usually come back with an error on your calculator in that case. Right, so please be aware of parentheses placement. Right. Okay, now look at the next example. Let's get rid of some of this stuff. Another one where I have a number to a fraction power involved somewhere. Alright, notice the parentheses. Alright, so the base on this power of 2/3 is all of this in parentheses here. So exponents 2/3, the base is the whole thing, is all of -64. Alright, now look at the denominator, right? Again, we're focusing on the index at first, right? The denominator is odd. The denominator on that power is 3. That's an odd number. So it doesn't matter if the base is positive or negative. This is a real number. We can find its value. Right. Now if that were 3/2, right, if it was 3/2, then it wouldn't be real, because I'd be taking the even root of a negative base, right, of a negative radicand. Okay, alright, so I'll just set this up the way I've been. Right, we have -64 to the 2/3 power, and I'm going to write this with a radical in it. I like to work with the denominator first, as you've seen. So what is this? This is, denominator is 3, so I'm doing a cube root of the base. So I'm taking the cube root of -64 first, and then taking that and raising that to the numerator. Right, so I take the cube root of -64 and then raise that to the second power. Alright, and what is the cube root of -64? So, what number to the third power would give me -64? That'd be -4. Alright, -4 to the third is -64, and then we're squaring this. And what is -4 squared? That's -4 times -4, positive 16. Right, so the value of that expression, this -64 to the 2/3, is positive 16. And let me just double check that here. Parentheses, -64 raised to the positive 2/3 power, positive 16. Fantastic. Great. And again, hopefully it's easy to how to change an expression with a fractional power into an expression with a radical. Just again, your denominator is the index of that radical. All right, and then one last one, well, not one last one, but one last one where we're actually going to be able to find the value without using a calculator so much is this one here. Here I've got -25. Now again, it's in parentheses underneath this exponent, so this whole thing is the base on that exponent. The base is negative, but right, look at the power. It's 5/2, 5 in the numerator, 2 in the denominator. That is an even number, right? So remember, I've been saying, you got even. You'll be taking the square root of -25. Can't do that, right? Even root of a negative number, even root of a negative radicand is not real. So this is, I would simply say, this is not a real number and be done with it. All right. Now, if you wanted, you can say, oh, maybe I didn't see that right away, and then try doing it the way I've been doing it, writing it as a radical. So first I'd be taking, the square root, right? The denominator is to the square root of the base, the square root of -25, and then raising that to the 5th power on the outside. But hopefully at that point you're seeing, the square root of a negative, right? Even root of a negative radicand, that is not going to be a real number. So I'd call it, I'd be finished, it's done. I'm just saying it's not real. And as I mentioned before, we're not going to get into imaginaries here just yet. That'll be for a future video. Imaginary numbers, non-real numbers. All right. Now, some of my examples we've been able to actually find the value of because there were nice, perfect, perfect squares or perfect cubes, right? Like this one here. When I wanted the cube root of -64, that was just -4. -64 was a perfect cube, right? There was a nice rational number, -4, that I could raise to the 3rd power to get -64. But that's not always the case, right? You don't always have a perfect square or a perfect cube or a perfect 4th power as your radicand. So you see this one here, approximate the expression. Notice it says rounded to 2 decimal places. Because look what happens when I try writing this. I've got 50 to the 2/3 power. Denominator on that power is odd, so this is going to be real no matter what the base is, positive or negative. It's going to be positive though. Right? It's an odd root of a positive number. But look what happens when I try to write this out, right? As a radical. I'd be taking the cube root of 50. Right? So the cube root of 50. And then after that cube root of 50, raising it to the second power. Well, 50 is not a perfect cube, right? Look at here are some perfect cubes off to the side, right? Now I'm just going to look at the positive ones. Yeah, I know -1 and -8 and negative 27 and so on are perfect cubes. But 1 is a perfect cube. You can write that as 1 cubed. 8 is a perfect cube. You can write that as 2 cubed, right? 27 is a perfect cube. You can write that as 3 cubed. 64 is a perfect cube. You can write that as 4 cubed. Well, notice how I passed up 50. Right? So 50, in between there, 50 is not a perfect cube. All right, and of course you could do any ratio of these, like the fraction 1/8 would be a perfect cube. You could write that as 1/2 cubed, right? And 8/27 would be 2/3 cubed and so on. But 50 is not on this list. So because of that, the cube root of 50, and again, we've seen this in previous videos. So the cube root of 50 is not rational, right? Is what they call irrational, and is not a rational number. Can't be written as a ratio of 2 integers. Can't be written as a fraction. So that's why we're asked to round to 2 decimal places. The cube root of 50 is going to have some decimal form that never ends and never repeats. Okay, and then we're going to be squaring that crazy number, and so really all I'm going to do here is like, this isn't nice. I don't know what this is, right? I don't know what the cube root of 50 is. It's not nice. I know it's between 3 and 4, right? Because 50 is between 3 cubed and 4 cubed, right? So the cube root of 50 will be between 3 and 4. So when you square it, this is going to be between 9 and 16, right? Between 3 squared and 4 squared. So let me just punch this in. I'm just going to punch it in as 50 raised to the 2/3 power. I'm getting this crazy 13.572088808, and I'll write that down here. Right? So 50 to the 2/3 power is 13.5720888, and so on. Again, it's irrational, right? Not rational, so it never ends, never repeats, and it has a repeating pattern. And what I'm asked to do is round to the nearest hundredth, right? 2 decimal places after the decimal point, tenths place, hundredths place. So we're focusing on this spot here, right? Rounding to the nearest hundredth, 2 decimal places, meaning we have to look at the 3rd decimal place, look at the thousandths place. If this was 5 or higher, I'd bump the hundredths place up by 1 digit, right? From 7 to 8, but it's not. This thousandths place, the 3rd decimal place, is less than 5. So I just leave the hundreds by the way it is. All right, so 50 to the 2/3 power is approximately, right? Notice when I round, I don't use the ... I use the approximately equal to the wave equal sign, is about 13 point, and then to the 2 decimal places, 57. All right. And that's what we're asked to write. Right? Approximate the expression rounded to 2 decimal places. Okay. Next one similar. Got the same instructions. I'm asked to find, round to 2 decimal places. Now this is kind of crazy, this one, but it's 40 to the 3/20ths power. All right, so if I were doing this the way I've been doing it, where I write it as a radical, look at the denominator of that. That's 20. That's going to be the index on the radical. I'm taking the 20th root. The 20th root index 20 of 40, and then raising that to the numerator, raising that to the third power. All right. I don't know what this is. What to the 20th power would be 40? So I mean, look at if you want to think of what are some perfect 20th powers. Now this is an even number, 20, so all of these will be non-negative, right? 0 you can write as 0 to the 20th. 1 you can write as 1 to the 20th. That's fine. But then 2 to the 20th power is huge, right? It's a very big number. 1,048,576 is 2 to the 20th. Well, notice how we have definitely skipped over 40. Definitely, right? 40 is not a perfect 20th power. So this is going to be irrational again, and we're raising to some power that's not a multiple of 20. So this is going to be an irrational number, something that's not a nice fraction, something with a decimal that never ends and never has a repeating pattern. So because of that, I'm just going to punch it in. Again, 40 raised to the 3 over 20 power. And we see it's going to be between 1 and 2. Right? We've got 40 to the 3/20th power equals 1.7390377 blah blah blah, right? Goes on forever without ending and no repeating pattern. But I have the same instructions, right? Round to the nearest 2 decimal places. So that's this place here where the 3 is. But remember, when we were rounding, you look at the place after it. I'm looking at the thousandths place. This time, it is higher, 5 or higher. So I'm going to bump this 3 up to a 4. We're closer to 1.74 than we are to 1.73. All right, so when rounding, we're getting 40 to the 3/20th power is approximately, 1.74. Great. All right, and that's it for those two. All right. So far we've seen these expressions where I have a base to a fractional power, and I've written them as an expression with a radical in it. The next few examples I have for you are going the other way around, where I have an expression with a radical, and I'm asked to write an expression, with a fraction power, a rational exponent. All right, so that's the next several examples, right? So I say here, write each radical with a rational or a fraction. Whenever you see the word rational, it's ratio of 2 integers, right? A fraction exponent. All right, so I'm going to take this one step at a time here. We did this last video as well. Remember when I have the 8th root of some, radicand? Remember the radicand in the radical expression becomes the base, and vice versa. Right? The radicand of the expression becomes the base when you write it in exponential form or with an exponent. So this 8th root of a cubed, the radicand is a cubed, so I'm going to put that in parentheses over here. All right, that's the base on what power? And the index is 8, meaning I'm doing the 1/8 power. And then I use that power to a power property. This is a to the 3 times 1/8, or the 3/8 power. Okay. And perhaps also, so the 8th root of a cubed is the same thing, means the same thing as a to the 3/8 power. Now you might also want to point out too, very often in an expression you like to point out what's allowed to be plugged in sometimes. What am I allowed to replace a with? So notice that we do have an even index, right? The index is 8. Same thing here. This is an even denominator on this power, telling me that I'm taking an even root. So that means that a, right, can't be, or a cubed in this case, right? A cubed can't be negative. Well, the only way a cubed will be negative is if a is negative. So one thing I'll put off to the side here is that, maybe we'll add to this that the value of a has to be greater than or equal to 0, right? Maybe add that to it, right? Because if a were negative, you would have some expressions that weren't real numbers, right? Be taking the even root of a negative. So a has to be some value replaced with some value greater than or equal to 0. So yeah, so keep that in mind. Sometimes it's nice to write that down. What am I allowed to plug in? What am I not allowed to plug in for my variables? Okay, great. Now this next one's a little trickier, and I'll explain why. Because of what the symbol means. Right? Now I can go through the same steps as I just did in the previous example, right? The radicand is t to the 12th, so I'll put that in parentheses here, t to the 12th. And what's the exponent? Well, the index is 4, so the power here is, to the 1/4 power. Put 4 in the denominator. And then what's 12 times 1/4? That'd be 12 fourths, right? T to the 12 fourths. But what's 12 divided by 4 though? That's a nice whole number. That's t to the 3rd power. 12 divided by 4 is 3. And I'm going to tell you this right now. You got to really, when there's an even index, I'll point that out again. This is an even number. When there's an even index, you really have to pay attention. You really have to be careful. Because I'm going to tell you right now, what I have just written here is wrong. The 4th root of t to the 12th power equals, just t cubed. This is incorrect, and I'll show you why. It's almost there. Right? It wouldn't be. It would be a good start to write this, but it's wrong. Let me show you why. If they're truly equal, right, that means they should be equal no matter what you plug in for t. So what if t were, say, -1? The left side, you have the 4th root of, -1 to the 12th. The right side, you'd have -1 to the 3rd. Now, a negative number to an even power is positive, right? -1 to the 12th would just be 1. So you have the 4th root of 1. Now, a negative number to an odd power on this side is negative. -1 to the 3rd would be -1. And it all matters about remember what the symbol means, right? When you see a radical symbol, I've said this a bunch and I'm going to keep saying it. When you see a radical symbol, right, when you see the 4th root of some expression a, remember this is what's the non-negative 4th root of a, right? But non-negative. Whenever you see this symbol, the radical symbol with an even index, the result on the other side can't be negative. It has to be non-negative. Well, look at what I'm getting here. The 4th root of 1 equals -1. That's incorrect. So these two expressions I've written here, the 4th root of t to the 12th and t cubed, they're not the same all the time. When you say two things are equal, when you say two expressions are equal, they have to be equal for every value you plug in, every value that's allowed. Well, there's a pretty simple way to fix this, and again, you saw that I put this up a couple videos ago on evaluating expressions of the form, the nth root of a to the nth, right? The nth root of nth powers. There's a very quick fix to this. Just use absolute value. Right? So the quick fix is just, okay, do what I did normally. Do what I did normally. But, t cubed, this can, just ask yourself, can this ever be negative, right? I'm seeing this symbol with an even root, so the other side can't be negative. You have to ask yourself that question. can this expression, can this be negative? Right? And if the answer is yes, it can, right? Yes, it can. Because, look at when t is -1, you get -1. When t is -2, you get -8, right? This expression can have negative values. So the quick fix to that is just use the absolute value. Just ensure that it will be non-negative. All right, and I've said it already. You've seen this in previous videos if you've been watching. So when I say the 4th root of t to the 12th, and I'm asked to simplify it, again, you can do what you normally, start off doing this. It's equal to t cubed, but you saw not all the time, not when that's negative, right? This can be negative, so let's just ensure that it's not by popping the absolute value symbols around it. So the 4th root of t to the 12th, it's not just t cubed, it's going to be the absolute value of t cubed, right? And this would be correct. That's the right way to write it. And these are always equal, right? Try -1 now, right? The left side will be the 4th root of 1, or 1, and the right side would end up being the absolute value of -1, which is also 1. You'd get 1 equals 1, which is a true statement. This statement is always correct, is always true. So yeah, so again, problems that you come across when you see even roots. Even roots are tricky. You always have to make sure the radicand is non-negative, and whenever you see an even root, not only can the radicand not be negative, but the result that you get on the other side, what it's equal to, can't be negative either. And then of course odd roots are simple, right? You can take the odd root of anything and get anything back. All right, so I have another example where I have a statement involving a radical, and I have to write it with a fraction power. All right, now I'm not seeing nothing crazy is going to happen this time, because last time I had the 4th root of something to the 12th, and 4 went into 12 evenly, so something it simplified a bit, and I had to worry about if that was positive or negative or whatever. 4 doesn't go into any of these powers, right? 4 doesn't go into 1, 4 doesn't go into 3, the BQ, so I don't really have anything to worry about here, like I did last time. So I'm just going to rewrite this with some fraction powers. All right, so this guy in the parentheses here, this base, the radicand is going to be the base, right? So in parentheses, I'll put this 12ab cubed. And that 12ab cubed, we're taking the 4th root of that. And as you saw in the last example, 4th root means raised to the 1/4 power. All right, and then this itself, so I'll use, you can use another set of parentheses. I'm using some brackets here. Then this thing itself, I'll put in the brackets, is being raised to the 9th power. All right, so I have something to a power, and then that again to another power. So we can multiply these two powers here. All right, the 9 and the 1/4. So that leaves me with the quantity, the original radicand, the base 12ab cubed, raised to the, and then 1/4 times 9 would be the 9/4 power, and there you go. All right, there's that original expression with a radical, written as an expression with a rational exponent. And I'll just, again, I'll leave it like that. And we can use other properties of exponents to rewrite this if you want, but I'm going to leave it like this because I don't want to get into other properties of exponents at this time. All right. Now my last couple examples, my last two examples have to deal with something I mentioned at the beginning of the video a while back, negative exponents. So I'll refresh your memory again here. When you see something raised to a negative power, it's just 1 over that same base to the positive power. And vice versa, when you see 1 over the base to a negative power, you can flip it over, say it's equal to the base of the positive power. So let's keep these in mind. In fact, I'll leave them up top here as we go through our next examples involving negative powers. All right, so rewrite, pardon me, So rewrite each of the following with a positive exponent, right? So wherever there's a negative exponent, that's what these rules are for, right? To take something with a negative exponent and rewrite it as an expression with a positive exponent, or vice versa, right? This expression, this side has a negative power, and I can rewrite it with a positive power, right? And then simplify, tell me what number it's equal to, if possible, right? If it's actually a real number. All right, so here I have 81 to a negative power. So first I'm going to rewrite this with a positive power. So this negative half is like the negative n, right, where n is a half. This is the reciprocal, 1 over, right, I'm just doing this rule up here. 81 to the negative half is just the reciprocal, 1 over 81 to the positive half. And, 81 to the half, 81 to the positive half, remember that's just the square root of 81, which is 9. So that means 81 to the negative half is, 1 over that, right? Is the reciprocal 1 over 81 to the half, 1 over the square root of 81, 1 over 9, or 1/9. Okay, and again, let's just double check that. Punch this in here. We've got 81 raised to the negative 1/2 power. Now you're going to see it's come up as a decimal point, 1111111. But if I go, I have a feature where you can change to a fraction. Hit the math button, change to fraction. See, it's really tiny, but it's 1 over 9, right? Like I got here. Fantastic. All right. So again, negative powers to positive powers, and then let me simplify. Same thing here. This time though, see how my negative power is not in the numerator like it was on this side, but it's in the denominator, right? So I'm using like this rule here. I have 1 divided by, and then 8 to the negative 2/3. Well, that's like this side of this rule. 1 divided by 8 to the negative 2/3. So a is the 8, and the n is the 2/3. This will be just equal to the reciprocal of the positive one. It's just equal to 8 to the positive 2/3. And these should be equivalent. Check it out. Check out the rule. Just replace n with 2/3, a with 8. All right, and then what is 8 to the 2/3? Remember how we work these. I'm going to rewrite this as a radical. The denominator is odd. It's 3. That's the index of the radical. I'm going to be taking the cube root of 8. Taking the cube root of 8, and then raising that cube root of 8 to the numerator power, the second. And what is the cube root of 8? That is 2, right? 2 to the third is 8. And then 2, what's 2 squared? 2 to the second, that's 4. So the value of 1 divided by 8 to the negative 2/3 should be positive 4. Let's see that work out here. Right, so 1 divided by 1 over 8 raised to the negative 2/3. You're seeing the number 4. Wonderful. All right, and then I have one last example here. Same thing, I'm asked to, now this time there's a variable, right? Notice now this is another one where there's just a single variable. So just like other ones where I've had just a single variable, I'm going to put down what values I'm allowed to plug in for that variable. Now notice in my fraction here, the denominator is even. So that means the base can't be negative. So 13 times x. 13 times x needs to be a non-negative number. All right. Also, can't be 0. All right, you're going to see when I rewrite this with a positive power. Remember this. This is like this rule up here now, where the a is 13x and the n is 3/2. So 13x to the negative 3/2 is just the reciprocal 1 over the positive power, 13x, again the base of 13x to the positive 3/2. So can you see how x can't be 0 also? So it's got to be a positive number, right? Because if x were 0, you'd have 0 in this denominator here, right? 0 to the 3/2 power. So off to the side, I'll write that. Right, the values I can use it for x are only positive. Right, I can only use positive values for x in this, and that's it. All right. And I say completely simplify. First I said rewrite with a positive exponent, which I have here, 1 divided by, and then you have this 13x to the 3 halves. But then simplify, 13 to the 3 halves. 13 doesn't have a nice square root. So really I can't do much with this. I mean, if you want to, you could write it with a radical. So I mean, I'll box this one in. This is perfectly fine right here. But you could also write this with a radical. 1 divided by, and then down here this is the square root of 13x, and then that thing is being raised to the 3rd power. Right? Remember the denominator, they take the square root and then cubed. But again, my value of x, when I plug in a value for x in these expressions, x has to be a positive number, because I don't want to be taking the square root of a negative number, and I also don't want 0 in for x, because I'll have 0 in the denominator, and remember, dividing by 0 is undefined. Okay, so hopefully you got, remember these rules for negative exponents, power to power, the relationship between radicals and fraction powers there. And, I'm hoping that raising a number to a fraction power is simple enough, right? I like taking the roots first, using the denominator first, and then raising to the numerator, as you've seen. Okay. And as I like to say at the end of these videos, do the best you can to learn the material on your own before you go looking for help. I find that people who take the time and the effort to learn it on their own tend to remember it better and for longer. So of course, read the material, read the author's examples, perhaps even work out solutions to some author's examples before you look at how the author did it. Then compare your work with the author's and see if you can learn from some mistakes. Obviously, work on plenty of exercises, practice problems, look up solutions to them whenever they're made available to you so that you can check yourself, track your progress. And don't give up on a problem after one attempt. Very often in mathematics there are several approaches that'll work for a problem. So if after several attempts, several approaches at a problem, you're still not seeing how to do it, still not getting it, perhaps you should read through the material and the examples again, maybe even a 3rd time, more slowly, more deliberately, take notes. Because if you've worked on some problems, there's a good chance that you have a better idea as to what the author wants from you, from that section, from that chapter, whatever. So going back and reading through you'll know better what to look for. And maybe some things will pop out at you that didn't pop out the first time, or some things will click in your head or make sense that didn't make sense the first time. But if after several read-throughs of the material and several attempts and approaches at problems, you're still not getting it, still not making sense, well then, it is not a sign of weakness whatsoever to go out asking for help. That is what other people are there for help. So ask a teacher, a tutor, a friend, someone in your class who you know knows the material well and is willing to help. Look for supplemental materials online. There's tons of it out there. Look for videos on the subject. There's loads of those too on math. Videos such as this one, or plenty of other ones out there that are better than mine. I assure you, you can find them pretty easily. But just keep at it. Don't give up. Stay persistent. Keep practicing. And above all, I think the hardest thing, and the one that makes the most difference, is try to have a positive attitude, a positive mindset, about the subject. If you go into something thinking it's going to be boring and you're going to hate it, and I've always hated it, you're probably going to continue to hate it and continue to think it's boring, and you're just not going to get anything out of it. But if you believe, have a positive attitude about it, if you believe that I'm going to learn something, you believe that you're going to take something away from this that's going to be useful in either your class or at work or in your life, whatever, or maybe even have fun with it, it's amazing that the difference a change in attitude can make for the learning experience. I know it's easier said than done, right? But just try to have an open mind. Try to have a positive attitude. So stay persistent, keep practicing, stay positive, and don't give up. Right? Don't ever give up. And I just know you're going to get it. Thank you for watching.